Hello, class. How are we doing? It's Professor Rourke here. I wanted to make a video for some of the material in section 10.2. I know it can be a little overwhelming. In particular, I'm looking at the interactive assignment for 10.2. I think chapter 10, and starting in everything, it can be a lot, but especially in chapter 10, I think it is a good idea to maybe start like organizing your information and sort of tracking things a little differently than some of the other previous chapters because there is so much going on. So to do that, I'm going to work through this problem with you, but I'm also going to sort of model how I would recommend you write your work down on a paper while you are doing your problems in my math lab. This I think is just like a good practice as we get towards the end of things and things can get more complicated, and then we can sort of help to sort of keep track of all of the information because there is a lot of information given to us. Okay, so let's go ahead and take a look here and see what we have. Okay, so your problem is probably very similar. This is technically the fifth problem in the interactive assignment for 10.2. And just a reminder, I know again, there's a lot of information, but what I typically recommend you do, if you get to a problem that you're supposed to solve and you're completely confused, I would go back a couple pages earlier in your interactive assignment, particularly look for the last example that you can find. And I am a big fan, I think I've told you this before, of clicking the show StatCrunch steps. I think that can be really helpful. I also think it's helpful to click show the result or watch the video. Okay, so like for instance, for this problem, this is number 5 in the interactive assignment, but really like 2 slides before is a like similar example in some ways, but also some of it is a little different. Okay, so that's one thing I just want to make a note of. Sorry, I'm losing my voice here. I think the allergies. Okay, so let's take a look at this problem. So researchers selected 833 patients at random among those who take certain widely used prescription drug daily. Take a certain widely used prescription drug daily. Okay. In a clinical trial, 23 of the 833 patients complained of flu-like symptoms. Suppose that it is known that 2.2% of patients taking competing drugs complain of flu-like symptoms. Is there sufficient evidence to conclude that more than 2.2% of this drug users experience flu-like symptoms as a side effect at the alpha equals 0.01 level of significance? And it's like, whoa, that's a lot of information. Okay, so what I'm going to do first is I'm going to go ahead and do a little split screen with the actual problem and what I would probably write down as notes, like if I was a student in this class. Okay, so let's read it again one more time. It says researchers selected 833 patients at random who take a certain widely used prescription drug daily. Okay, so even in that first sentence right there, that's a lot of information, right? So they tell us that's our sample size, right? So I would probably write down on my paper, okay, N equals 833. But like, what is the sample, right? And this kind of ties me back to like the first test where it says, it maybe gives you like actually like kind of similarly long problem. And it says, maybe you'll ask you, what's the sample? What's the population? What's the statistic? And what's the parameter? Okay, so a lot of that is very similar to what is we really need to kind of do here. Okay, so yes, the sample size is 833, but like 833 what? Right? And I know sometimes I get tired of writing like all of the words. So I understand if you don't necessarily write all the details. But what we're talking about is patients who take a certain widely used prescription drug. So I'll just kind of abbreviate a little bit. I'll say patients who take this RX. I'll say RX. I feel like it sounds a little bit more formal than just like take this drug. um, Okay, so then I'm also sort of thinking at the same time um, that the population would be all patients who take this one certain widely used drug, right? Prescription drug. So the population is really all patients. Now, it's kind of weird because we don't know what drug this is. We don't know like patients where, right? Like all patients in America, all patients in the world, but we can assume that if it's widely used, that's probably a lot of people who use this prescription drug daily, okay, or whatever it is. Okay, you can pretend it's something that you recognize. I don't know. Okay, so then it says in a clinical trial, 23 out of the 833 patients complained of flu-like symptoms. Okay, so right there, that's telling me because we often, when we're setting up these as like proportions, right? They give us this sample and then they give us like a part of that sample that had some characteristic, right? Sometimes they call it like number of successes, right? Which is a little strange because I don't think a success would be having flu-like symptoms, right? Like in how we think of a success, but it's what we're looking for. It's what we're tracking, okay? And so that's what we call X, and sometimes again it's called number of successes is 23. So 23 of these 833 patients complain of flu-like symptoms. Then it says, suppose it is known that 2.2% of patients taking competing drugs complain of flu-like symptoms. Okay, so what they're saying there, and again, only because it takes some practice, they're telling us our null hypothesis there, right? They're saying, suppose it is known, right? Sometimes they word it different ways, but what we're going to say is that we'll assume that this is correct, right? Suppose it is known. Sometimes they'll say the CDC states, or sometimes they'll say, I know, previous records show this, right? And so what we usually do is we accept that as correct, right? We'll say that we think that 2.2% of patients with that take a similar competing prescription drug experience these symptoms. Okay, and so 2.2%, we do want to take that. It's already a decimal, like it already has a decimal in it, right? But it is a percent, right? So we have to take this percent and actually turn it to a complete decimal form at a percent. So we can take 2.2, we can divide it by 100, or sometimes people like to say they like to move the decimal place 2 times. And so however you want to think about it, I believe that would be 0.022. Okay, that is going to be the assumed to be true null hypothesis that with these types of prescription drugs, you can expect 2.2% of patients to have these flu-like symptoms. Not great, probably. They probably wouldn't, I'm assuming, continue it. I don't know. We don't even really know, aren't given a whole lot of context here. Okay, so then it says, is there sufficient evidence? So that's like where my like ears perk up. So I'm like, okay, they're getting ready to give us what the alternative is. Okay, is there sufficient evidence to conclude that more than 2.2% of this drug's users experience flu-like symptoms? Okay, so this is what we call like the alternative hypothesis. Sometimes they say H sub A, sometimes they say H sub 1. And what they're trying to say again is that they're trying to conclude if there was more than 2.2%. Okay, so we're trying to prove or see if there's enough evidence to suggest that actually the proportion of users who experience flu-like symptoms is higher than that. Okay, so I know that's a lot of information, but this is again what I would recommend you sort of start writing down because it is a lot to keep track of. And especially just sort of like going back and forth and like clicking around and maybe go to StatCrunch, it can be very overwhelming. All right, so this is what I would recommend is you write down what is the sample size, but also like what are we even talking about, right? Like this the patients who take this prescription. X is the number of successes, and I would even probably, if I was like a real studious person, I would say these are people who like experience these symptoms, right? And then we also were given the null hypothesis because it says suppose that it is known that that is 2.2% of patients experience these symptoms. So this is our null hypothesis that P equals 0.022. And the alternative is saying, is there sufficient evidence to conclude that more than 2.2% of the drug users experience flu-like symptoms as a side effect? And they even give us alpha. Okay, they say alpha is 0.01. Okay, so sometimes we use alpha. Sometimes we're given alpha. Sometimes we're not. Out in the wide world, you actually pick your own alpha. Like if you were making up your own study, you would actually decide what you wanted the bar to be. And so remember, it can get a little tricky, I know, in 10.1, but alpha is supposed to be, it's the probability that we make a type 1 error. So that would be that we reject the null hypothesis when we shouldn't. So we really want to make sure we try not to do that, right? Because they compare it to finding someone who is innocent, um, guilty, right? We really that's our whole justice system is set up that we try to avoid that and minimize that risk, right? This is assuming that this is all flawed, the world is flawed, and we're trying our best, right? But we really don't want to try to say, you know what, this 2.2% is wrong, it's different when it's not, right? We really want to kind of make sure that we have a high set of evidence, right? Like in the civil court, right? It's like a preponderance of evidence. And then, so that's like, okay, probably happened in terms of like a court of law, right? Versus the criminal is like beyond reasonable doubt. So like, we really need to make sure that there is no chance that that there's a doubt that the person did it, right? And so that's kind of the equivalent of alpha. If there's a situation that doesn't really have a lot of effects, that's kind of like the civil court. Like you can set your alpha to be a little larger if you want to really minimize it, like kind of like the equivalent of a criminal case, then you would want to make sure your alpha is really small. And so this alpha is very small. Long story short is we want to really make sure we want less than 1% chance that we screw this up, that we reject when we shouldn't. Okay, so I know that was a lot of information. That was just setting the stage. Okay, here we go. Now the conditions, my least favorite part ever in the history of all this class. This part here, right here, is my favorite. Okay, so it says, because n times p sub 0 times 1 minus p sub 0 equals blank, blank 10. Like what? Okay, so this is the other beast of these of all of these problems is not only does it a lot of information, but these conditions, let me tell you. Okay, so no matter which order you really think of them in, it's okay. But there's really like 3 conditions. And the reason we have to do all this is still all the way back from chapter 8. And even actually this one started all the way back in chapter 6 when we were looking at binomial. And we were really doing this to make sure that we could say that we're building this all off of a sampling distribution, right? So we're saying that we can build a sampling distribution off of this information, and it should be approximately normal, is what it all really comes back to, this whole normal curve. But we have to make some rules. And our textbook in particular has a certain way that shares, it's similar to other textbooks, but honestly, like if you go out into just like the wild world and look up some of these conditions, like on AI and things like that, they might not line up exactly. So that also can be confusing. Okay, so the rule of 10, I just gave it that name because I don't really know how else to think of it, but it does sort of help that we're saying that the sample size times the proportion, the assumed to be true proportion, times 1 minus the proportion. It's got to be greater than or equal to 10. And so sometimes they even write it as n times p times q must be greater than or equal to 10. So that's usually like the most annoying part to check, I think. Here, the problem wrote it as 1 minus p. And sometimes they say q, those are interchangeable, right? It's just like the complement all the way back from chapter 6. So that's why I do kind of like the end, everything sort of ties together, but it can be overwhelming too, because you're like, oh gosh, was I supposed to remember that? Okay, so this is where, again, I would just sort of identify everything. N, remember, we wrote this down, hopefully, and that would be 833, right? And then P here is just going to represent whatever the P sub 0 is. They're saying like that's whatever the proportion is that goes with the null hypothesis. Okay, and so the null hypothesis, again, I know there's a lot of different things happening, but again, I would just try to see if you can write these down for me. The null hypothesis was the 0.022, okay, the 2.2%. That's what we're gonna, again, assume is true. That's what we're using to check our rule of 10. And then we also, sometimes I like to do this as separately, it's just to state straight out what Q is, which again is just 1 minus P. And this is where like it is helpful to have a calculator, even though we do most of the actual calculations inside of StatCrunch. Like these little things are helpful because I don't really feel like saying 1 minus 0.022 in my head. No, thank you. Okay, so long story short is we have to multiply 833 times 0.022 times 0.978 and see what we get, and it should be bigger than 10. Now, as I mentioned, some other textbooks say this differently. Sometimes it all goes back to the central limit theorem, right? Where we just need to make sure that we have a big enough, the larger the sample size, the more normal your distribution will be. So here, because we have such a big sample size, like I feel like we could probably, some textbooks would be like, yeah, this is good. This is fine. We don't need to worry about it anymore. But our textbook makes it a little bit more complicated and breaks it down into this like special combination that's saying that, okay, yeah, we get a big sample size, but if our P is really small, like honestly, our P is pretty small here, this proportion, it could maybe actually not be bigger than 10, even though your sample size is really big. It is specific and it is annoying, but it's okay. Okay, and so we multiply n times p times q, so that's 833 times 0.022 times 0.978, using our calculator again. And I'm also kind of looking to see, because this one always gets me, sometimes they like the rounding of that number, they sort of can be a little funny about, but it just says at the bottom, it says round to 1 decimal place. Okay, so if I multiply all those, that comes out to be about 17.9. Okay, and that's greater than or equal to 10. Yay. Okay, so again, I know it's annoying, but it is sometimes also kind of helpful because it does sort of force you to make sure you have all your ducks in a row right in the beginning. Okay, so I don't love it, but it's fun. Okay, and so this one is always has to be greater than 10. That's just what the rule of 10 is. I put greater than or equal to because you know how it is. Now that we're in like proportions, the difference between 10 exactly and 10.000001 is really, there's no difference really. So a lot of times, sometimes you'll see greater than, sometimes you'll see greater than or equal to, and it's really it's not making a difference either way. I'm sorry again, my dogs are barking. Chaos. Okay. But then we get to the other annoying condition, but it's fine. Okay, so we always want the sample size to be big, but we don't want it too big, which I know is like, oh my gosh, there's too much happening. But this one we usually just sort of be like, yeah, yeah, yeah. Okay, sure. Okay, we don't really actually have to compute anything here. So we want the sample size to be big again, for the rule of 10, but then also you don't want it so big that you're risking sampling the same people over and over again. This is all built again off the sampling distribution where we can take like a huge number of samples. The idea is that we should be able to take a lot of samples. And if we're taking, like if we're talking about a population of 100 people and we're taking samples of size like, I don't know, 25, well, we're only really going to be able to get out 4 samples. That's not gonna, without sampling the same people over again. So this is where they came up with this other rule where they said the sample size has to be less than or equal to 5% of the population. But a lot of this is just like, okay, sure. Because this where it comes back again to what we were saying before. We're like, okay, N is these 833 patients, right? That's my sample size. But what is the population? Well, it's all patients who take this widely used prescription drug daily, which again, it's sort of vague, but I think because I say it's widely used, like we're supposed to assume that's not going to be a large number of people. I'm trying to think of like what's the most commonly used prescription drug. I don't know. It could be anything. Let's just say allergy medicine. Okay. Some specific prescribed allergy medicine, and we have millions of people who take this. Then 833 is definitely less than 5% of that, right? And so a lot of times that's just sort of like, yeah, okay. So then we'll say the sample size is less than 5% of the population size. And the patients are, and this is supposed to be my third condition, where it's supposed to be, a random sample, pretty much. That's usually kind of like the go-to. So then we go back and see. Sometimes we'll say it'll straight up say it's random, or sometimes we just sort of assume it's random. So we'll look for, a lot of times we'll say it's like if it's stated to be random or can reasonably assume to be random. And so this one here says at random, and so they say they were selected at random. Again, just sometimes they make it a little bit more complicated. They're like, it was stated to be random, or we can assume it's to be random. So things like that. Okie dokie. So all of these are satisfied. And spoiler alert, they are always going to be satisfied if we have more things to do, right? Like otherwise we would stop there. We wouldn't really be able to go further. Now we could talk about like some things sometimes you'll see studies, maybe they weren't able to get a big enough sample size and they like say that could have affected the results, things like that. But for all of these, these nicely kind of curated problems, even though if they seem complicated, we're going to assume that the conditions should be there for if we're supposed to keep going, right? Okay, so then this is where we get into our null and alternative. And this is where hopefully in the beginning, if you wrote everything down, it sort of flows nicely from it. So because this is a percent problem, right? You're talking about 2.2%. That's a clue that it's going to be a proportion, right? So we do the first obstacle is to make sure that we select P for a proportion. They also have in here U. That would only happen if we had like we're talking about the means of something, like the average. I'm saying means, so I just want to make sure like we understand that we're talking about like a list of data, maybe, or they say like the sample mean is this, and this is the sample standard deviation, and they tell us what the population mean supposed to be. We don't have that. That's all we focus on is either proportion or a means question. And so this is a proportions question because it says 2.2%. It's sort of the clue. Sometimes it'll straight up say proportion in the problem, right? But here it just has percent, so we can assume it's going to be P. And the null hypothesis is always equal to. Okay, we're always going to assume this is correct, that whatever the suppose it is known 2.2%, our null is always equals to. The alternative is where we get a little different. So here they said H sub 1 for the alternative. I had H sub A, and so we'll say the proportion is greater than 0.022. Okay, that is all just still based off of those first pieces. We still haven't really done anything, right? Like even though I mean we have, but it's been a lot just to get there. Okay, so now we can finally go and calculate things in StatCrunch. And I know again these can be overwhelming because if you click to solve this and like view an example, it's like cool and all, but it's a little tricky. I think the conditions are good. They do walk you through there. But then once we get here, they go into this really long, complicated test statistic formula, which really, it's really like a z-score, right? It's just saying what is the assumed to be true proportion, and like so it's x minus the mean divided by the standard deviation. However, we don't have to find this by hand. It's not bad to understand like where it's coming from, right? But we don't have to. We can use StatCrunch to find all of this. And it says, well, either technology or formulas and tables can be used, use technology. And so, I know again, it can be very overwhelming. Pretty much anything past here, past the null hypothesis, you can do everything in StatCrunch. And that's what you really want to do, especially for a test in this accelerated course. It's great to do these by hand and to use the formula or to understand the formula that it's really all just a z-score with proportions, the same z-score thing we've been doing from the beginning. But we can find this the most accurately and most efficiently in StatCrunch, right? Okay, so here we are. And it's really the same steps as what we did in chapter 9. If it's a proportion, we go stat, proportion, stat. If it's a means question, like it's going to happen in 10.3, we do stat, t-stat. We actually never need to do z-stats for anything. If you continue into studying statistics, there is a slight delineation between when you use t-stats and z-stats, but t-stats is really the way that our textbook chooses to always use, because if you remember, the t-curve and the z-curve are almost identical. It's just that the t-stats give a little bit more wiggle room whenever we're taking sample data to predict the population or to make these inferences. So pretty much we always use t-stats. But okay, I'm sorry, this is getting quite long because I'm rambling about a few different things here. But okay, so we have proportion stats, and then this is also still one sample with summary. If it was with data, it would be a list of 833 patients, and it would be like flu symptoms, no flu symptoms, no flu symptoms, flu symptoms for 833 pieces of data. We don't have that. Okay, so we're going to go proportion stats, one sample with summary. When we come back in chapter 11, the good news is everything really kind of repeats itself, but we will have two samples. So we'll be comparing two different populations, and that's when you'll just do proportion stats, two samples. Okay, so we do one sample with summary, and this is where you'll see like, oh, it's set up exactly with what we had. And especially again, if you write things down, I think it really lends itself well to being able to kind of clearly enter this into StatCrunch. Okay, so number of successes, again, is 23, sometimes called X. not a success to have a flu-like symptoms, but it's what we're focusing on. So it's what they call a success. It's like, oh, okay, yeah. Okay. And number of observations is 833. And remember back in the day in chapter 9, we would select confidence interval, but we don't do that here. We don't want a confidence interval based off of that sample data, although sometimes they do actually have us do hypothesis testing with confidence intervals. But here they want the test statistic, they're going to want a p-value. So we just leave it on hypothesis testing. And here we'll go ahead and change this proportion to the null hypothesis is 0.022. Okay, so whatever we had for our null hypothesis, we just enter that value in here. And you do want to change it to make sure it matches that we're talking about if there was more than 2.2%. So our alternative is greater than 0.022. Okay, and once you have that, that's all you need. You just go ahead and click compute, and let's see what we have. So sometimes the pop-outs are like woo, overwhelming, but this one's not so bad. Okay, not as much. So it's talking about proportions. They just kind of repeat that the count was 23 and the total was 833. This is the sample proportion. If we wanted to, see like, okay, what is 23 divided by 833? Like, what is that as a percent? And it would be 0.028. So like 2.8%, right? So there was a larger number of people in our sample than 2.2%, but like, is that enough to say that it's definitely higher, right? Like that's what the whole question comes down to be. Because maybe we just had a sample that had slightly higher flu-like symptoms for a variety of reasons, right? Sampling distributions are spread out. They're not every sample is going to get us exactly 2.2%. It's going to be varied, right? And how is it going to be varied? Well, this is the standard deviation, right? So like if we were to make the sampling distribution, it would have based off of our data, the number in the middle would be 0.027 and the standard error would be 0.005. But this is the test statistic here. So 1.01, right? So we can go all the way back to z-scores and think about, like our normal curve all the way back from chapter 3, really. This is saying this is like one standard deviation above. And you can already start thinking, like, is that unusual if I have a z-score of 1.1? No, right? Like when we start talking about unusual, it's got to be at least like farther out than 2 standard deviations. So we can already start thinking there, like, okay, this is not that unusual based off of what we're told. It wouldn't be weird for us to have a test the sample data. Okay, if 2.2% was correct, this is not weird. Okay, that we got the data that we got. Well, that's what we're looking for, weird stuff, things that are like really rare and weird. That's when we have enough evidence. Okay, so the test statistic, again, is BAM is right there. And then the p-value is also boom right here. So the test statistic, that is what you could use the z-score formula for, but I don't really recommend it. I really don't. Like, I just feel like we have enough to do. It's not the worst thing in the world. It's just a little bit tedious. Oh, and I didn't round correctly. Let's see. It says say the p-value would be 1.135. Okay. Now this is the whole reason we did all of this is to see whether we reject or not reject. Okay. And then this is again where I would maybe go back to my notes and really sort of start thinking that just writing it down because it really does follow the same pattern every time, even if it really doesn't feel like it. Okay. So again, I wrote everything down from the beginning, and now I'm going to go ahead and add on to here what this all means. Okay. So let's see how I can do this. So what this is saying is that my p-value is 0.1348. Okay, so the whole idea again is that if this p-value, the p-value is, let's see if we can get this right, is assuming 2.2% is correct, right? That's how many people you would expect to have flu-like symptoms who take this medicine, right? Assuming that's correct, we're assuming that's true. If we took our sample data and we got the samples that we got, right, which technically had 2.8% as the rate of people who experience these symptoms. Is that weird? Like, is that rare? Because if a 2.2% is correct and I took a sample and I did a good job, and the probability that I got that value is like super unusual, like almost impossible, probably. Then you have enough evidence to reject the null. But if your p-value is not unusual, then you don't reject. Okay, I know it can be a lot to keep track of. The shortcut is if the P is low, you reject the hoe. Okay, and it's got to be lower than the alpha. That's where the alpha comes in. Okay, so if the P value here, this is like a big idea. If this is is like if P is low, if this is lower or like less than alpha, okay, you reject. Okay. If it's not low, you don't reject. So then we look at again at our alpha here was very small. Our alpha was 0.01. Like that's like 1%, right? So we're saying we want more than unusual. Unusual, usually we say like 5%. We want this to be like super unusual in order to reject because we really don't want to reject when we shouldn't. Okay. So we look at our p-value. Sometimes it helps me to think of this as a percent. 0.1348 is actually like, if you think about it, like 13%, that's not low, right? We're talking, we need it to be lower than 1%. We need this number to be lower than 0.01. So is the p-value low? No. Okay, it's not low. So we fail to reject the hoe. Okay, so what the heck does that mean? If we fail to reject the null hypothesis, that means there was not sufficient evidence to support the alternative. Okay, whatever the alternative is, which was this, that the proportion was actually greater than 0.022, we do not have sufficient evidence for that. We don't have it. Okay, because if P is low, you reject the hoe, we have sufficient evidence. If the P is not low, we fail to reject the hoe, there's not sufficient evidence. They all go together. They go together each time. So if P is low, you reject the hoe. There's sufficient evidence to support the alternative. But we don't have that here. We don't reject the hoe. There is not sufficient evidence to support the alternative. And that is really, I know again, this is a really becoming a really long video because I know I'm taking a really long time to kind of go through it. But I'd like to think about that first and then try to deal with the mess of the drop-down menus. Okay, so again, I would really recommend to write this down in a way that makes sense to you. And that way, when you come back and try to put the pieces together, hopefully it feels a little less overwhelming. Okay, so it says, since the p-value is, okay, is the p low? No, p is not low. 0.1348 is not low. So it's greater than alpha. So that means we do not reject the null hypothesis because if the P is low, we reject the hoe. It's not low, so we do not reject the hoe. Okay, and that means there is not sufficient evidence at the alpha equals, we just repeat the alpha 0.01 level of significance to conclude that more than 2.2% of the users who take the prescription drug daily complain of flu-like symptoms. Okay, so that second part there to conclude that is really just stating the alternative. Okay, so when we have it really like we'll say we have sufficient evidence or we don't have sufficient evidence, and then we just state the alternative. So the alternative claim again was that more than 2.2% of users experience flu-like symptoms. So we just like repeat that. Okay, so we're saying that we don't have sufficient evidence to support that. Okay, I'm so sorry that this video has been so long, but I just really wanted to kind of like make sure we took some time to go through it piece by piece and what I would recommend. Okay, so just to recap, I know again, it was a lot. And so I'll put timestamps on this as well so that hopefully it maybe can kind of help because I know again, it is quite overwhelming. Let me go back to this problem. Okay, so first thing first, I would really recommend you go off on the sides and write down what is the sample size? What is the population even supposed to be, right? What is X, the number of successes given? That's all the sample data given, okay? And then we then keep reading to get what is the null hypothesis? So it'll be like, it is known, right? Or the CDC says, or, it's something that we're basing this off of. And so for here, and they just redid this they repopulated a different problem. We would write that is what we assume to be true is the null, and then they'll always state the alternative, usually like kind of in the last little sentence there. Okay, so once we have all those pieces down, we go through, we get through those painful conditions, which I know are necessary, but are so painful. Okay, and then once we get through that, really it's just to StatCrunch we go. Okay, that's how we're going to get out the test statistic, the p-value, all that. And then once we have the test statistic and the p-value, the probability out from StatCrunch, we can put the pieces together. If p is low, you reject the hoe. there is sufficient evidence. If P is not low, you don't reject the hoe. There is not sufficient evidence. So they all just sort of go together. I try to put that in the announcement in case that helps. I feel like, especially trying to get started on these things. All right, real quick, I'm just going to flip through to number 6 real quick, just to kind of show you and what this would look like. It's really the same thing, but it just looks different because there's like much less stuff, right? But same idea, right? It's just that they kind of cut all the words out and just said, okay, do this hypothesis testing. Here's the null, here's the alternative, here's my n, here's my x, and alpha is 0.1. Okay, unfortunately, we still begin in the same place where we have to do the lovely rule of 10, which, does, I think, I'm trying to always stay positive. It does help us to really make sure we have our ducks in a row, right? So here, P is 500. I'm sorry, N is 500 and P is 0.85. So what I would recommend you do, again, is just to kind of go off on the side, even though I know it's a little less confusing. Hopefully that they have the values spelled out for us. I still like to kind of go off to the side and say, okay, N is 500, P is 0.85, 1 minus P is 0.15. And so then that way I can just go to my calculator and say, well, N times P times 1 minus P, all I have to do is 500 times 0.85 times 0.15 and see what that comes out to be. And here they say not to round. Like, okay, fine. All right. I mean, I guess that might be a little easier. I don't know. But this comes out to be, just using my like simple calculator, is 63.75. And again, I really would only kind of use the calculator for these parts and then use StatCrunch for the rest. I think it really is great if you can complete these with the Z formula, but then you would still either need a table or StatCrunch to find the probability. So I think it just makes sense, especially again, because the accelerated course, that we just do this all at once. Okay, now this one is a little different than the last one because it actually asks you for the sample proportion. The last one didn't ask us that. It didn't say what are, like, based off the data we have here, what proportion have, no, I don't want to leave. Have these symptoms. They don't give us anything, no words here, but they ask us for this. So that one's not bad. Hopefully, like in theory. We could also, if you remember, if we just want to put this right in the StatCrunch will tell it this to us if we don't even want to do this. It did come out in that table what the sample proportion was, but we can do this, right? It's usually it's not terrible. So it's talking about taking whatever the sample was and actually finding its sample proportion. So it'd be like 410 divided by 500. Is it weird that I actually kind of missed the words, like the context of like, what are we talking about here? Like I didn't really love, the whole thing with the commonly used prescription drug, but at least it helped give me like an idea of what we were talking about, but that's okay. Okay, now they say go to the test statistics. So this is again where if you click view an example, it's going to show you the z-score formula for proportions, which is really just like the null hypothesis. I'm sorry, our sample proportion minus the null hypothesis divided by the standard deviation, which is that it's kind of complicated formula, P times 1 minus P divided by N, take the square root. We don't really have to do that. We've suffered enough. We have enough to do. Okay. And so we can just go ahead and pull up, let me clear this off just so we can sort of see everything. I'm going to pull up StatCrunch again. And again, remember it's stat, proportion stat, one sample with summary. And we can just go ahead and say number of successes is 410, number of observations is 500. They told us already the null hypothesis is 0.85, and we're trying to see if there's enough evidence to say that it's not 0.85, which always cracks me up a little bit. Like, you're like, I don't know, is it less or greater? I don't know. It's just not that. Okay, and so again, the test statistic is negative 1.88, which we can sort of see here. That's not that rare, right? If we have a z-score of negative 1.88, it's close to -2, right? So it's almost to -2. It's close, but it's technically not, it wouldn't be super rare, but it's like a little bit rare. It's close to -2. And so this p-value is kind of interesting because it's 0.0603. And so let me go ahead and put that in there. Let's find the p-value, 0.060. Okay, So this in like a percent would be like 6%, right? And so this one's like one of the ones that's kind of like on the line because it's not greater than 2 standard deviation, right? Because the z-score was negative 1.9, like we like round it, right? So it's almost there. And it's not less than 5%, right? So with that information, you would be like, oh, it's not unusual, right? But then this is where it gets a little weird. They chose alpha as zero point 0.1. That's a pretty big alpha. So things must not be that important because they're saying like, okay, I want my sample statistic to be like rare, but not, it doesn't really have to be that rare, like I just want to make sure it's like less than 10% chance. And so we have to look to see is 0.06 or like 6%, is that less than zero point 0.1? Is 6% less than like 10% essentially? If P is low, you reject the hoe. And so I would argue this P value is really not that low, like in life, in the scheme of things. Usually we're looking for like less than 5%. The last problem was like less than 1%, right? But because they give us the alpha is zero point 0.1, then yeah, the P value is lower than 0.1, right? So the p-value is lower than zero point 0.1. So p is low. We reject the hoe, and there is sufficient evidence to support the alternative. So it says state the conclusion. And again, I know that was a lot of information, but I just want to, this is the opposite of what we had before. So this one, the p is low. Okay, it's not that low, but again, it's lower than alpha. I'm just going to kind of make sure it's saying. So whenever the p is low, you reject the hoe. And this means that there is sufficient evidence to support the alternative. Those go together every single time. Okay. If P is low, you reject the hoe, there's sufficient evidence to the alternative. If P is not low, like we saw before, you fail to reject the hoe and there is not sufficient evidence. So pretty much the only difference is everything is like this, but negated. So P is not low. You do not reject the hoe and there is not sufficient evidence is the other option. So here we'll say they just go straight to the chase. Do you reject or fail to reject? We reject the hoe because the p-value is less than alpha. But bam, bam. Okay, so again, I'm so sorry this was so long. I hope you can maybe use the timestamps because I know that was a lot of information, but I hope this really helps in some ways just to kind of get the hang of things. You're so close to being done. The only thing we really have left now that we're here, like this is it really. The next section is with means. So all of the same information that we have before, all of these rules about P is low, reject the hoe, all of that stays. Pretty much the only thing that's going to be different is we're going to use P-stats. And the conditions are a little different, but also similar. There's no rule of 10 in 10.3, so that's good, And then in chapter 11, everything really just repeats, but with 2 samples. So we'll do proportions, like in terms of StatCrunch, 2 samples, and T-stats, 2 sample. And then that's where we end things, is analyzing these two population proportions and two population means. So we are so close to being done. I know these ones can feel overwhelming. So please, 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 I would really recommend, if you can, to have a running side log on your notes, which you might need more than you have had in the last few chapters, especially where you write down what is the sample, what is the number of successes, what is the null hypothesis, what is the alternative, get those stupid conditions out of the way. And then really just keep writing down if P is low, reject the hoe. That means there's sufficient evidence. If P is not low, you fail to reject the hoe. There is not sufficient evidence to support the alternative. I know it just sounds like a whole bunch of hogwash right now, but I feel like once you really kind of practice it and like I think see it over and over again, hopefully it'll feel a little bit better. So thank you guys so much. Please keep up the great work and let me know however I can help. I am here for you. And I'm always happy to help with however I can. Okay, thanks.